In this video, we will analyze rotations in the plane with respect to a Cartesian basis, and we will discover what the famous rotation matrices look like. And once we have derived those matrices, we will confirm that they satisfy the four properties we discovered in an earlier video that rotations themselves satisfy. At some point along in this video, we will make use of these trigonometric identities. And I know that a lot of students begin to feel very nervous when they see a trig like this, so I'd like to make a couple notes. First of all, there is nothing to worry about. We will only use these identities a couple of times, and they're in no way central to the subject of linear algebra. On the other hand, trigonometry is a wonderful subject in its own right, and very useful. So I encourage you to embrace trigonometry and to learn it well. And if that's what you decide to do, then you can consider this discussion as a first great step towards that goal. If you have a hard time remembering these formulas, our discussion will actually provide you with a way of memorizing them. And actually not so much memorizing them as being able to figure out what they are on demand whenever you want. In fact, if you're wondering where these formulas came from, and for this formula you already know the dot product analogy, we'll discuss it a little bit later, but if you ever wondered where these really came from, then you will see that the discussion that we're about to have will actually serve as a perfectly legitimate derivation of these trigonometric identities. So if you're uncomfortable about these or you don't remember them, just pretend you don't know them at all. And towards the end of our discussion, we'll be able to turn it on its head, where you will see that these identities are actually the outcome of our discussion. Okay, any other points I'd like to make? No, let's get on with the derivation of the rotation matrices. These are simply matrices that represent rotation in the plane with respect to this basis. So we'll follow the procedure that we always follow, which is to consider the basis elements, apply the transformation to each one of them, decompose the images of the basis vectors with respect to the same basis, and put the components of the decomposition in the matrix. So let's see what we get. It's a very simple task. We'll start with E1. We'll say that's the angle alpha. And so, oops, let's draw it a little bit straighter. All right. Not my best effort, but there it is. This is R sub alpha of E1. I'm just going to sneak a peek at the viewfinder to make sure it fits okay. Oh, it fits perfectly. Okay, so this angle right here is alpha. Of course, it's unit length, just because we're rotating a vector. That's unit length to begin with. So the components of this vector are completely straightforward. And we've had this discussion more than once before. And it's cosine alpha, sine alpha. So the first column of the matrix is cosine alpha, sine alpha. So here we go. Cosine alpha, sine alpha. So I'm using R sub alpha to denote this matrix. It would have been more consistent to make it R sub alpha comma C, because this matrix represents the transformation with respect to this basis. But everything is in this discussion is sub C, and so we'll skip it just to save space and make the formulas on the board a little bit more neat. Now, if we were talking about different bases, then you would definitely have to indicate what basis we're considering. But this whole chapter basically focuses on Cartesian bases with little detours, one of which we'll take in the next video. So it's okay to leave it like that. Let's just remember that it's with respect to this Cartesian basis. Let's move on to the second column, where we have to rotate, this will be in the way, the second basis vector by the same angle. That's not bad. Right here. So this right here is the angle alpha. This, of course, is R sub alpha of E2. And its components are minus sine alpha, cosine alpha. You can kind of see that this segment is the same as this. And even though my drawing doesn't show it perfectly, this one is the same as this, except it's in the negative domain. So we have negative sine alpha, cosine alpha, negative sine alpha, cosine alpha. And here it is. This is the so-called rotation matrix. For obvious reasons, it represents rotations. And it has a lot of very nice properties. So we'll discuss its more general or less general, I don't know. I won't categorize the properties. Let's start with these 4 properties and make sure that they're satisfied. And then we'll move on to some other properties that have to do with length preservation properties of rotations. So first, let's confirm this. So that's the part that will take a little bit of trigonometry. So I reserved space here for r beta, r alpha, and we'll see what we get. Hopefully, it'll be r sub alpha plus beta. Not hopefully, definitely. So here we go. Here we have cosine alpha. I'm just copying it down. Negative sine alpha, cosine alpha. I just want to make a quick note because you saw me peeking up to remember what the matrix looks like. I frequently forget what the matrix looks like. I remember it's full of sines and cosines with a floating minus sign, and it's hard to remember where it is. So whenever I need to remember what this matrix looks like, I close my eyes and I just remember the first half of this drawing, just r of E1. I just visualize E1 being turned by the angle alpha, and then its components, of course, are cosine alpha, sine alpha, and that's the first column. And once you have the first column, you have the whole matrix. So practice it a couple times. Close your eyes, visualize this, and you should be fine. And here we have r sub beta. So it's the same thing, but with beta. So cosine beta, sine beta, negative sine beta, cosine beta. Now let's see what we get. In this entry right here, we have cosine beta, cosine alpha, minus sine beta, sine alpha. Or if I did it in alphabetical order, cosine alpha, cosine beta, minus sine alpha, sine beta, and lo and behold, it's this formula right here. So what we get here is cosine of alpha plus beta. We're off to a great start. Number 2, how about this entry right here? We have, for this entry, it's this row and this column. Minus, I'll do it in alphabetical order this time, minus sine alpha cosine beta, minus cosine alpha sine beta. This formula right here with a minus sign. So we have minus sine of alpha plus beta. It's as if these 2 formulas were tailor-made for dealing with rotations. Moving on, this entry right here in alphabetical order, cosine alpha sine beta plus sine alpha cosine beta. Once again, this formula, and we have sine of alpha plus beta. And just for my pleasure, let's get the last entry here, which is minus sine alpha sine beta plus cosine alpha cosine beta. So I hope you enjoyed it too, but we have cosine of alpha plus beta. So let's look at what we did in 2 different ways. Here is way number 1 to look at it. Way number 2 will be the much more interesting way. Using these trigonometric identities, we have verified that r sub beta, r sub alpha equals r sub alpha plus beta. So this has been verified, and actually, because the second and the third are consequences of the first one, if you remember, we have verified them as well. That's one way of looking at it. Another way of looking at it is we never doubted this identity in the first place. So we knew that this matrix, which represents the rotation by the angle beta with respect to a Cartesian basis, times this matrix does the same thing but by the angle alpha, must equal the matrix that represents rotation by alpha plus beta with respect to the same basis. We knew this was true. There is no reason to verify it. That was almost like, what is it called? Sanity check. If we would be in big, profound trouble if this didn't work. We never doubted this. We know this works. So we know that this matrix times this matrix must equal this matrix, just because due to the fundamental nature of this identity. So what we actually just did was derive these formulas. We just derived them. In fact, a great way of looking at it is not that we used them to derive this matrix, to come up with this matrix, but we actually derived these identities from these calculations, because we know that this matrix times this matrix must equal this matrix because of how fundamental this is. So there you go. That's a great start for trig. You're off running with trigonometry. And another thing I just wanted to mention has nothing to do with this discussion, but it has to do with the dot product. That's just on the subject of memorizing this formula. If you recall, cosine of alpha plus beta, which is alpha minus beta, is the angle between two vectors. So that one is easy to remember because it represents the dot product. You get alpha 1 beta 1 plus alpha 2 beta 2. In other words, cosine alpha cosine beta plus sine alpha sine beta. So you just put a minus sign in front of beta, and then this formula presents itself, which is alpha 1. Now alpha plays the different role. It used to be a coefficient. Now it's the angle. A little bit confusing, but you can keep it straight. Alpha 1, alpha 2 minus alpha 2 beta. Alpha 1, what did I say? Alpha 1 beta 1 minus alpha 2 beta 2. So just another way to memorize this formula. But I think that this is much better. If you ever forget it, just write down these two matrices, and here's your formula for the cosine, and here's your formula for the sine. Or maybe this entry is better, then you don't have to deal with that minus sign. Right here is your formula for the sine. So there you go. So this property has been verified. This follows straight from this, so there's no reason to check it. This also follows from the first one, if you recall. I just wrote it down differently. Now let's talk about there being no eigenvalues. We have to confirm that this matrix right here has no real eigenvalues unless alpha is a multiple of pi, in which case you have -1 or 1 as your eigenvalues. You can review the earlier lecture to see where that came from. So there are two ways of doing it. I'll show you a somewhat elegant way of thinking about it. Let's use our easy eigenvalue giveaways to analyze this matrix. If you recall, the product of the eigenvalues equals the determinant of this matrix. And what is the determinant of this matrix? Actually, number 1, it will be something nice. Number 2, it has to be something nice. If you remember, and we will remember, our discussion on length-preserving linear transformations. But without further ado, the determinant of this matrix is cosine squared alpha plus sine squared alpha. The two minuses cancel. And of course, it's 1. So let me write it down right here. Determinant of R sub alpha is 1. It's a very fundamental property that we'll see across rotation matrices, whether it's in 2D or later on in 3D. That means that the product of the eigenvalues, should they exist, must equal 1. So they're sort of like x and 1 over x, or lambda and 1 over lambda. Now, what's their sum? Well, before we look at their sum, if one of them is lambda, then the other one must be 1 over lambda. That's what I just said. Okay? And their sum, again, I'll just make sure things fit. They do perfectly. Okay, so that's what their sum is. So assuming they're positive for a moment, what's the smallest this expression can be? What is the absolute smallest this expression can be? If you think of its graph, where can I sneak in its graph? Right here. Then near 0, 1 over lambda dominates, and further out lambda dominates, so it looks like this. So the question, what is the absolute smallest it can be? That's a calculus problem. So I'll save it as a calculus exercise for you. But once you do this exercise, find the first derivative, equate it to 0, find the point where that occurs. That will be at lambda equals 1. And that will lead to the conclusion that the smallest this expression can be is 2. That's the smallest it can be. Now let's get back to the matrix and from the trace property figure out what the sum of the eigenvalues is. And of course it's cosine alpha plus cosine alpha, 2 cosine alpha. So on the one hand, the least it can be is 2. On the other hand, it's less than 2 because cosine alpha is less than 1, unless alpha is a multiple of pi. So that tells you that unless alpha is a multiple of pi, and for multiples of pi, this matrix is either identity or minus identity, so there is very little analysis to do. But unless it is a multiple of pi, there are no real eigenvalues. There you go. So this was easy without doing it the other way, which is to figure out the characteristic polynomial. It will be a quadratic expression. Find its discriminant and make sure that its discriminant is always less than 0 unless alpha is a multiple of pi. We could have gone either way. I think this is a more elegant way of doing it. So we're done verifying these 4 properties. What I'm going to do next is erase everything, and we'll spend a little bit more time talking about the inverse of this matrix and how it relates to the length preserving properties of rotations. All right, here it is. Here is the inverse of R sub alpha. And as we know, all we have to do is plug in minus sub alpha. Excuse me, plug in minus alpha. Because if you were to multiply this matrix by this matrix, you would get cosine alpha minus alpha, sine alpha. So it will be the same matrix with zeros plugged in. And of course, that's the identity matrix. So this matrix times this matrix is in fact the identity matrix. So this is the inverse. And just a couple of words about how I obtained it. I plugged in minus alpha for alpha, and cosine doesn't care, and sine becomes negative of itself. So this is the inverse. And so all that happened is that minus jumped from here to here. And that's when we notice something that we've talked about before. And it was a very significant result with very significant implications. With minus sign just jumping from here to here, what we got is the transpose of this matrix. This matrix is orthogonal. Its inverse is its transpose. Let me write it down. That's very significant. R sub alpha transpose. There you go. So the inverse of this matrix, and that will be the case for all rotation matrices with respect to Cartesian bases. When I say all rotation matrices, I'm thinking ahead to going into 3 dimensions. They will have this property. Had we not had that original discussion, we would think of it as a marvelous coincidence that we would be very happy about. But since we did have that discussion, we're absolutely not surprised, because this is the statement that rotations preserve lengths of vectors. Whatever the length of the vector was before the rotation, that's what its length is after the rotation. All linear length preserving transformations have this property. So of course this matrix, which represents one particular such transformation, has that property as well. But importantly, the 4 properties that we have discussed previously were properties of the transformation itself. So they didn't depend on the choice of bases. This comes from the Cartesian property of the bases. So if we were to choose a different basis, and that's what we'll do in the next video, we will preserve the other 4 properties, but we must unavoidably lose this one in general. And of course, this, the determinant being 1 or minus 1, in this case 1, also has to do with the basis being Cartesian. So we will also lose this property most likely. So once again, to repeat, rotations have a lot of properties. Those properties are reflected in the matrices that represent rotations. However, some of the properties, some of the representations depend on the choice of bases and others don't. Length preservation and the transpose being the inverse depends on the choice of bases, so we will lose it once we lose the Cartesian bases. The determinant being 1 depends on the choice of bases, so we will lose it. Now I'm thinking. Okay, I'm going to take this one back because there's something more profound about the determinant. We could suspect losing it, but we actually won't lose it, of course. What am I saying? I take the whole thing, everything stays except for my statement about the determinant, because number one, the determinant is the characteristic of the linear transformation and not so much its matrix representation. And of course, it equals the product of the eigenvalues. Here we don't have any, but this, not depending on the choice of basis, is a little bit more profound. So the 4 properties that we had before, plus this one, stay. The property, the orthogonal property that says that the transpose in the inverse goes. So that's rotations in the plane with respect to a Cartesian basis, and the big oops, which I'm happy you got a chance to see.